All right, so let's look at some practical applications for using our energy equations. So if we look at, say, a skier, we'll put a little jump in there, and at the bottom. So if we have our skier up here on their skis and they're getting ready to start, they've taken the ski lift up and they're up there, and we say that we know, let's say we know the hill is 100 meters high, and we know at this point is 30 meters. And we know that the total energy of the system, which means the skier going off the ski jump, okay? If we know the total energy of the system is 50,000 joules, what else can we know about this system? So if the total energy equals that, we know from our formulas before, total energy equals potential energy plus kinetic energy. And we know that potential energy equals mass times the acceleration of gravity times height. And kinetic energy equals 1/2 mass times velocity squared. So if we're simply given that the total energy of the system is 50,000 joules, we can figure out a couple of things. We can say that at the top of this system, where the person has gone up and they're waiting at the top of the hill and there's no motion, at this point we can say the total energy is equal to the potential energy plus the kinetic energy. We can say that at any point on our ski run. But at this point, we know that the kinetic energy is 0 because the velocity is 0. So we can say that at the top, before any motion starts, the total energy is going to equal the potential energy. Or the potential energy equals the total energy, if you want to think about that. And so it will equal 50,000 joules, the potential energy at that point. So we can also say that down here at the lowest point, at the end of the system, right, we can say that the total energy will equal the potential energy plus the kinetic energy. Remember, we can say that at any point. It's always, the total energy is always going to equal potential plus kinetic. And it's in our perfect physics world, the total energy at the end is going to be the same thing as the total energy at the beginning. But at this point, when they're at the bottom of the hill, the height will be 0, so our potential energy will be 0. And so the total energy at this point will equal all kinetic energy. Energy has all been transferred to motion. So if there's no motion, the total energy equals potential energy. And at the bottom of a motion, when all of it's been converted to velocity, all the energy, the total energy of the system will equal the kinetic energy. So down here, I can say the kinetic energy is 50,000 joules. So what else can I determine? If I know that the potential energy is 50,000 joules, and I know that potential energy equals mass times the acceleration of gravity and height, I can figure out the mass of my skier. I can divide my 50,000 joules by 9.81. All right, so I'll rewrite it so you can see it. So if this is potential energy, I can say that 50,000 joules, I want to determine the mass of my skier. So I'm going to rearrange this. I'm going to divide it by the height, which is 100 meters, times 9.81 meters per second squared, the acceleration of gravity. So I can determine that the mass of this skier is about 51 kilograms. So if I know the mass of the skier, and I know the acceleration of gravity, and I know the total energy, I can figure out the potential energy at any point on this, on her run here. So say I want to know when she skis down the hill and she gets here, she's not quite at the bottom of the hill, right? She still has a height, so that means she still has potential energy. but what would her potential energy be at that point? So at this point, the potential energy is still going to equal its mass times the acceleration of gravity times height. We determined her mass. Hopefully that hasn't changed on the ski run. So 51 times 8.1 meters per second squared times 30 meters. So we can determine that the potential energy at that point is 15,000 joules. So if the potential energy at this point is 15,000 joules, what is the rest of the energy? Because we know the total energy of the system is always going to be 50,000 joules. So we can say that, just like I said, we can say on anything, the kinetic energy plus the potential energy always equals the total energy of the system. So we've determined the potential energy at this point, and we can now figure out what the kinetic energy is at this point. So it would be the kinetic plus that 15,000 joules that we figured out. So if we rearrange this, we would see that the potential or the kinetic energy is 35,000 joules at that point. Those two numbers added together are going to equal the total energy. So at this point in it, we figured out that run, and we figured out the potential and the kinetic. So let's say that, so we can do that at any given point. So let's say our skier goes over a little jump here. So goes up the hill and does a beautiful, graceful arc before landing at the end here. So if we have this here, and let's say she went up another 30 meters, so she's 60 meters in the air above the lowest point of the slope, we can again figure out her potential energy. Her potential energy is going to be a 60 here instead of a 30, so her mass hasn't changed. The acceleration of gravity hasn't changed. Only her height has changed. And so we can change that there, and we can figure out that her potential energy at this point is 30,000 joules. So if we can figure out her potential energy, we can again find out her total energy, because the total energy, or her kinetic total energy, is going to equal kinetic plus potential. So potential is 30,000 plus kinetic is going to equal 50,000. So the kinetic energy at that point is 20,000 joules. But let's say we want to determine something else about this. What else could we figure out? We could figure out her velocity. Let's say we want to know her velocity here at the end. We know that we still have her, so we could do 1/2 times her mass, which is 51 kilograms, times the velocity squared equals 50,000 joules. Okay. We want to get our velocity squared alone to figure out how fast they're going at the bottom of the run. So you're either going to divide both sides by 1/2 or multiply both sides by 2, whichever makes you more comfortable. So if we multiply this side by 2, we can see we'll multiply this side by 2, then we multiply this side by 2. Multiplying 1/2 by 2 makes the 1/2 disappear. And then in order to get the velocity squared alone, we would divide by 51 kilograms. And that gives us the velocity squared. So in order to find the actual velocity, we then need to take the square root of all of that. And looking at the units, we would see that the joules are kilogram meter squared per second squared divided by kilograms means that we would be left with meters squared per second squared. So you can see that taking the square root of that would give us a velocity in meters squared per second squared. So I haven't done the math on this one, but if we did the math here, we would see 50,000 times 2 divided by 51 kilograms would give us the square root of 1960.8. And we'll take the square root of that, 1960, and that equals 44.3 meters per second. This, of course, is meters squared per second squared. So I had a pretty fast clip going down that hill. So I hope that makes sense to you. One of the things in the book they do a lot of times is they don't give you the mass of an object, and as long as it's the same object going through that whole motion, we don't really need to worry about it because the masses will cancel each other out. And I'm going to work through a problem in a second. Well, I'll work through the problem now. So on one of the on your ends, it's the one with the bike, he talks about the biker, how fast is the biker going, but he doesn't give us a mass. I don't have the book, but I'm going to see if I can recreate it here. So you can see how that works. So I think we have a biker, maybe up here, riding his bike. I know you guys probably want the handlebars there. So he's riding his bike down the hill. And we are given a couple of things. We're given a height of 21 meters. And we are given, maybe that's it. And so they want to know what speed he is going at the bottom. And so pretty much all we know is that at this point, right, he's not moving, so we can say the total energy is going to equal the potential energy, which is going to equal the mass times the gravity times the height. But we don't know his mass. So we can say that it's equal to the mass times 9.81 meters per second squared times 21 meters. So the potential energy is going to be equal to 206 meters squared per second squared times his mass. Doesn't matter what his mass is, because unless he wrecks his bike and loses a limb, his mass is going to be the same at the beginning or at the end. So at the second point, we can still say that the total energy of the system is going to equal the potential energy plus the kinetic energy. And so this second hill is 12 meters. And so we can say that the total energy equals potential energy plus kinetic energy. And so the potential energy at this point, at point B, is going to be the same thing we just did. The potential energy will equal his mass, whatever it is, times 12 meters times 9.81 meters per second squared. And we know that the total energy equals the potential energy plus the kinetic energy. Sorry, trying to follow my notes here. So the total energy of the system is going to be this, so 206 meters squared per second squared times the mass. And we're going to leave his mass alone because we didn't know what it was. We'll just leave it there. So the total energy of the system minus this number here, which was 88.3 meters squared per second squared. I'm wrong, sorry. It's 117.7 meters per second squared is going to equal the kinetic energy. So this was our total energy. Rearranging this equation, total energy minus potential energy will equal kinetic energy. And this one, again, we didn't know the mass here, so that's still times the mass. So those have the same units, so we can subtract them, giving us 88.3 meters squared per second squared times the mass, we're still going to keep that as our units, is going to equal 1/2 the mass times the velocity squared. So hopefully now you can see that our masses are going to cancel out. If we divide this side by mass and that side by mass, that will just make the masses disappear. They'll cancel each other out because his mass didn't change. And so we can see that this number is equal to 1/2 the velocity squared. So just like we did before, either divide by 1/2 or multiply by 2. Okay, to get that, I'm going to multiply by 2 because I don't like to divide by fractions. And that gives us velocity squared. And again, we're going to take the whole square root of that to find the velocity. So it turns out that the velocity equals 13.3 meters per second. So I hope that helps determine if you don't have a mass for something, you don't really need it because it's not going to change at this point. Unless he picked up something or he's making a delivery, the mass of this system didn't change, so we can do that.